Hello friends, we will be covering the following: diffraction, that is bending, diffraction pattern mathematical calculation, Brewster's law, polarization of ray, Malus law, Doppler's effect of light, difference between interference and diffraction, sunlight is unpolarized. We will study about that as well. Diffraction. In simple terms, diffraction means bending of light. Okay, diffraction is a phenomena in which light wave bend towards the shadow area whenever it passes over an obstruction. We'll see in these experiments. In picture 1, we have taken a candle as a source of light that will pass through the cardboard hole and fall on the screen. This hole is actually smaller. So what we have taken here is, this is a candle, this is a cardboard, and this is the cardboard screen. So we can say it's a screen, it's the hole. So the hole is small. When the light passes through it, we will observe that on the cardboard screen, this impression of the light is little bigger. So this is diffraction because the light has actually bent from here. It hasn't gone just straight to straight. It will bend a little, and this this thing will be little bigger. Impression of the light will be bigger. So let's to clarify this further, see what happens is, if this was the cardboard, instead of light going straight, you must have observed in the torch as well, so light actually spreads like this. So this bending is called diffraction. The bending of the light is called diffraction. Now look at this case 3. In this case 3, we have placed an obstruction in front of the split hole. Suppose this was the split hole. We have not allowed, there is no hole here. We have actually put an obstruction here. So what do we observe here? Still some light from the corner of the split. From here, from the corner, the light board comes out through this and can be seen as a point object on the screen here. Instead of light just going straight and there is only light in this direction, that's not the case. Though this part is an obstruction, the light still bends in this corner and we can see as a point light on this point. In case 4, if we bring screen closer, instead of keeping it that far, we bring it closer, then instead of point object, more light can be seen on the screen. But if you see, the light has been bent here in this direction. The light has been bent in outward direction. So this bending phenomena, the phenomena of bending of light around the corner of small obstacle, is called diffraction of light. Diffraction pattern. When light wave passes through a single opening, then the different sources having secondary wave, we get a bright and a dark spot of fringe. This pattern is known as diffraction pattern. So this is the single opening from where the light is going to come on the screen. So what do we observe? That in the center, this part, this is a complete diffraction pattern. So light in the center happens to be a little brighter, and then you can see there are fringes ahead also. This becomes a pattern of the light. So here in this picture 1, this is the picture 1 we are noticing. We have used a single opening and the pattern formed on the screen is shown to you. The same pattern. If we want, instead of horizontal, we can just keep it on the horizontal side like this. This is the vertical same pattern. We have kept it in the horizontal direction for you to see. This is the pattern how it is. So the fringe width in the center, this fringe width, is twice 2 lambda d by a, is twice than this. So the single width, we are going to derive that, but the single width is lambda d by a, and the width in pp center, this is the from the center point here and from here. So the center width is 2 lambda d. So the fringe width formula is lambda d by a. In diffraction, the center width is bright and double the width size. It's double the width size. So it is 2 lambda d by a. From picture 1, only the screen is kept here for you to understand the pattern. So this is just for your understanding. We have to actually kept the screen here. In the next slide, we will calculate dark point and bright point. We will also zoom into triangle ABN to calculate the same. So we are going to zoom into this part to calculate our bright and dark fringe. Again, let me just tell you, lambda represents the path difference. This AB, which is the slit of the cardboard from where the light can enter, this slit's value is A, small a. This is small a. What is the capital D here in the formula? Capital D is the distance between this cardboard and the screen on which we are taking the impression. So coming on to the dark point and the bright point calculation. Diffraction pattern, mathematical calculations. We are going to do first the dark point. So here we know A sine theta. What we have done actually, if you see this complete pattern we have seen on the other screen, we have only taken this AB, this one, ABN. So we have enlarged here ABN for your understanding. This was the distance A of the slit where the light can pass through. This is angle theta. So in here, A sine theta is lambda, 2 lambda, and on the way n lambda. So this is the path difference. So what is the path difference? Let me show you once again. For the dark point, see, we are calculating this Bn now. This is one path from where the source is reaching the point P. This is the other source which is reaching the point P. Here we are taking Bn. Okay, so we are going to calculate the Bn, which is the path difference. So here A sine theta equals to lambda, 2 lambda or n lambda. The value of theta is y by d. Where what is y? The value of y is here. Okay, so we calculate d is equal, theta is equal to y by d. So once we substitute this value y by d into in place of sine theta, we get a dot y by d equals to this. We just carry it down, lambda, 2 lambda, on further on. So our first dark fringe will be formed. Y1 will be equal to lambda d by a. This will be our first dark point. Okay, this will be our first dark point. So this is how it's an even multiple. Now when we calculate the bright point, so for bright point, A sine theta equals to 2n plus 1 by 2 lambda. This value is not lambda anymore. It is 2n plus 1 by 2 lambda for the bright point. So if this is the value and we put the value for theta is equal to y by d, then substituting this value here in sine theta, we get a dot y by d equals to 2n plus 1 by 2 lambda. So the first bright fringe formed will be 2n plus 1 by 2, which comes from this formula, keeping y on one side. So y1 is equal to this lambda comes down, d from denominator it goes up, so d by a. So this is the formula that becomes. So it's an odd multiple. What answer do we get? We get 3 lambda by 2, 5 lambda by 2, 7 lambda by 2. So the bright fringe is being formed in the odd multiples, and even multiple is having the dark points. Coming on to Brewster's Law. The angle of incidence at which a beam of unpolarized light falls on a transparent surface is reflected as a beam of completely plain polarized light is called polarizing or Brewster's angle. It is denoted by IP. Now try to understand, I will be explaining the term polarized light, but just explaining you a little. What happens is the light travels in like this, it travels in all the directions. So I will be explaining it to you. That is called a unpolarized light. But when it is a polarized light, then it is going to move only in one direction. So what is we are referring here is the angle of incident. What is the angle of incident? The ray that is coming. This is the ray that is coming, which is a beam of a ray. So we are denoting it by IP. Why we are calling it IP? Because it is a ray that is coming, it is the angle of incident at which a beam of unpolarized lights fall on a transparent surface is reflected as a beam of completely plain polarized light. So it will become a complete polarized light. How? Normally when the light comes like this is the refraction pattern. This is how, if it is a transparent surface, it must reflect back like this. Here, this light, when it touches this surface, some of the light actually reflects back. This reflection of the light, when it is reflecting back, is actually now a complete polarized light. The particle in it is not moving in multiple directions. It is moving in only one direction. This is a complete polarized light that is coming out from here. This is a complete polarized light. At the polarizing angle, the reflected and transmitted rays are perpendicular to each other. This is the reflected and this is the refracted. So the angle between these two is 90 degree. This is the angle that is 90 degree between them. And tan IP will be equal to sin IP by cos IP, or we can say sin 90 minus IP. So here this is, if you say tan is equal to sin IP by sin 90 minus IP, which is equal to sin I by cos IP. So we are actually trying to derive this, how this is 90 degree first to you. See, sin I by sin R equals to sin IP by cos IP. Here we can write sin R because this and this IP gets cancelled. So we have sin R is equal to cos IP. So cos IP can be written as sin 90 minus IP. So here R is 90 minus IP. So it means that IP plus R will be 90 degree. So here we are getting the value that this is also 90 degree, this is also 90 degree. And tan IP is equal to mu IP by sin R. Sin IP by sin 90 minus IP is equal to sin IP by cos IP, which is tan IP. Here mu depends upon lambda. So IP depends upon wavelength lambda. Trying to understand the polarization of light. So here, first of all, look at the picture. When I said that the light is moving in various directions, look at this picture. This is how unpolarized light is moving. See, it's moving in various directions. So once we keep the analyzer in between, so then the light direction is only which is filtered out is only in one direction. This is how it's only in one direction it's going to filter out. So unpolarized light has vibration in all directions. So it vibrates in all directions. This you can see, it's vibrating in all directions. If we somehow obtain a light that does not vibrate in all direction but only one, we can say it is a polarized light. So if only one direction, say here, when it is filtered out from here and the path is only one, it's only moving in this direction, that will make it a say polarized light. Shouting, this is just to tell you the EM waves, how it comes out. We have a separate chapter for that. So I hope this polarization light is clear to you. What we are trying to say, this unpolarized light, which has a vibration in all the directions. So this unpolarized light in this Brewster's law, when this IP light is passing from here and hits a transparent surface, there is an angle which is formed, which is a reflection and refraction. This is 90 degree in difference, and this ray that is being formed is actually becomes a polarized. It is moving now only in one direction. This is what the Brewster's law tells you about. And this is the various formulas that we derive. So these are just actually just mentioning that the difference is 90 degree. Okay, coming further, coming on to Malus law. This picture has an analyzing which is rotating. When light passes through polarizer, then through analyzer, then intensity is proportional to cos square theta. Theta is the angle between transmission direction of polarism and analysis. So what is happening is, this is a light, you know, light has vibration in all direction. So when this has got vibration in all direction, this is being polarized here, and this analyzer further is actually rotating. So when this analyzer is rotating, then I will be proportional to cos square theta. This is Mole's law. Intensity of the polarized light is equal to IP, that is the polarized light, cos square theta, angle between plane of transmission and polarizer. Okay, this is just a formula. Sometimes a question comes on it, so you need to note down the formula as well. Doppler's effect of light. Whenever there is a relative motion between source of light and observer, the frequency of light received by the observer is different from the frequency actually emitted by the source. The phenomena of apparent change in frequency of light is called Doppler's effect of light. So you have also studied Doppler effect in your class 6th or 7th, where we have mentioned about a very simple example where a moving train, you are standing on a platform and there is a moving train. So, or you're sitting in a train and you see another train which is actually moving, but you feel that your train is moving. This is the Doppler effect. So similarly, in terms of the light, what it is saying is, whenever there is a relative motion, there is a motion between there are two motions happening between source of light and the observer. So source of light is also moving and the observer is also moving, or at least one is moving. The frequency of light received by the observer, what the observer is receiving, is different from the frequency actually emitted by the source. So what was the frequency at the time when the source emitted is different than what observer gets it. The phenomena of the apparent change, whatever the change in frequency of light, is called Doppler effect of light. So in terms of light, here we have the formula that you can note down. So what are the values here? V is equal to apparent frequency, this part. Okay, so we are trying to calculate the apparent frequency, what observer sees. This was the real frequency of the source from where the light was being generated. V is relative velocity between source and observer. This is the relative velocity because both have movement. So there is a relative velocity, or at least one has got movement. So there is a relative velocity between the source and the observer. C is the velocity of the light. This C is the velocity of the light. Lambda is the wavelength. So if they approach each other, then it's going to be positive. If they move away from each other, then it's going to be negative. The formula that we derive is here. So the apparent frequency increases when the source and observer approach each other. When source and observer move away from each other, the apparent frequency can be obtained by replacing V by mu in above equation. Then it will be read as this. Okay. When source and observer approach each other, positive sign is taken as lambda minus lambda dash is positive. That is, wavelength in the middle part of the visible spectrum shift towards the blue region. This is called the blue shift. So you can study the concept of blue shift from here. This is where the blue shift concept is coming down. I hope this was helpful to you. Thank you.